Hi everyone, welcome to week 7 of live session for concentration inequalities. Um, yeah, since none of you are here, I think it's better to call it just a session. It's not live. I mean, I'm live at the moment, but yeah, when you see the video, it won't be live. And it's September the 10th today, and in this session, I will discuss assignment 6. So let's start. So the first question is, let x comma y have joint distribution P, where x is x1 comma x2 and y is y1 comma y2. And all these variables x1, x2, y1, y2 belong to x. Okay, and we want to say which of the following options are true. So here we are looking at this probability of x1 not equal to y1 given x. So recall that x is both x1 comma x2. All right, so this would be a random variable. I mean, the square of this is also a random variable, and so we take expectation, right? And we want to argue about this quantity. So now, okay, so let's write this as expectation, this probability here. So what would this probability be? This is just expected value of indicator function, I mean indicator of x1 not equal to y1, right, given x, the whole square. Okay, so what we have is, for all these options, the LHS becomes expectation of this indicator x1 not equal y1, okay, given x, the whole square. Yeah, that's it. Okay, so now you can use Jensen's inequality, right? And there are two ways of using Jensen's inequality here because there are two expectations, and between these two expectations is the square factor here. Okay, so now one way to apply Jensen's would be take this square inside this conditional expectation. And so what conditional Jensen's will give us is that conditional Jensen's uh, this will give us that this, okay, so let me denote this as LHS. So LHS is left hand side. LHS is less than equal to expected value of uh, expected value of indicator whole square, right? Indicator of x1 not equal to y1 whole square. Right, and we know 1 square is 1 and 0 square is 0. So this indicator square would be indicator. So let me just remove the square here. Okay. And which is just, so now we use this tower property of conditional expectation, that expectation of conditional expectation is just expectation. So what we get is expectation of indicator x1 not equal to y1, which is just probability of x1 not equal to y1. Okay, so what we have argued is that uh, this conditional, this average conditional probability, right, this quantity, the square of average conditional probability is less than equal to uh, the probability. Okay, okay, so this was one way of applying Jensen's inequality, where you took the square inside. Now there is another way of applying Jensen's inequality, which is you take this square outside this expectation, right? So this one would be like conditional Jensen, and this is the usual Jensen. There is no conditioning in the outer expectation. So if you take uh, yeah, so let's see what Jensen's gives us, which is on outer expectation, on outer expectation. Okay, so that will give us that the left hand side, um, now in this case, like, inequality would be reversed. Okay, so um, because we are taking the square outside, right? So LHS is greater than equal to, right? We're taking the square outside, so it's something like expectation of x square is greater than equal to expectation of x the whole square, right? So it's something like that. And here what we had was that expectation of x given y the whole square is less than equal to expectation of x square given y, right? So that was what was conditional instance. Okay, so now let's come back to Jensen. So here LHS would be greater than equal to expected value of indicator x1 not equal to y1 given x, right, and the whole square. And now, so it's basically this the whole square, right? So what is the thing inside the parenthesis? Just probability that x1 not equal y1, right? And so what we get is that this is equal to uh, probability x1 not equal to y1 the whole square. Okay, so option B and option C are correct. Yeah, yeah. So let's go to question number 2. So question number 2 is for a discrete set x, let P be a product distribution of x on x power n, and let Q be a distribution which is absolutely continuous with respect to P. Okay. Suppose x is equal to this x1 comma xn has distribution P and y has distribution Q. Let P be a coupling of P comma Q. Let so now we define this Hamming distance between x and y. Okay, it's just the number of coordinates at which x and y differ. Then which of the following are true? Okay, so we have this Hamming distance between x comma y, right? So this is I equals 1 to n, indicator of xi not equal to yi. Okay, and we take expectation of that. So this Hamming distance is a random variable, right? And when we are taking the expectation here, what we are assuming is, I mean, so both x and y are random variables, and so they are coming from this broad distribution x comma y, this coupled thing, this p, right, broad p. Uh, and again on the right hand side we'll have expectation with respect to the same thing. Okay, right. So we see that expected Hamming distance is just sum of probabilities of I equals 1 to n, right? Probability that xi not equal to yi. Okay, so option A doesn't seem correct. It's like it says probability. So you know that um, this is greater than equal to I equals 1 to n probability xi not equal to yi the whole square, right? Because probability lies in 0 comma 1 interval, so its square would be less than itself. Okay, yeah. So basically the option A is not correct. So now option B, C, D, they all involve the square of the expected Hamming distance. So let's look at this. So we have expected Hamming distance the whole square. Okay, now instead of writing this whole square, I just write square like this. Um, okay, so what would that be? That would be expected value of I equals 1 to n, indicator xi not equal to yi, the whole square. Okay, and somehow we want to bring in this pi xi not equal to yi the whole square, right? That kind of quantity. So yeah, so uh, okay, so now what you can write this in internals, the thing inside expectation. This is a summation, right? And we can also write this as Okay, so if you just take this, right? So if you have like three positive numbers a and b, a, b, and c, right? And so okay, so okay, why am I arguing all this? First, let me apply Jensen's inequality, right? That seems the obvious thing to do. So yeah, so by Jensen's inequality, we are taking the square inside. So Jensen's inequality would be this: xi not equal to yi, the whole square. Okay, right? And now look at this thing inside. So if you expand this, uh, yeah, you will have like indicator functions of xi not equal to yi, and then you'll have some cross terms. Okay, so and we know this result, right? If a, b, and c are three positive number, then a plus b plus c the whole square, this is less than equal to a square plus b square plus c square, three times that, right? And this is also basically Jensen's inequality, because how do we see this? You can write a plus b plus c the whole square as a plus b plus c by 3 the whole square times 3 square. Okay, we multiplied and divided by 3 square. And so now the thing inside is an expectation, right? It's expected value of a random variable which takes a with probability 1 by 3, which takes value b with probability 1 by 3, and which takes value c with probability 1 by 3. This is just the average of a b. So if you apply Jensen's here, so this is square of average. So Jensen says that this is less than equal to average of squares. Okay, so we take, right, so this is average of squares, and then into 3 square, right, which gives you this. Okay, so yeah, let's apply this here. So we have um, right, or maybe okay, so let's do it again. So what is, since, yeah, so since the thing is we want this probability xi not equal to y the whole square in all the options. So yeah, so this is basically this, right? I've included this parenthesis, and this is basically then I equals 1 to n probability that xi not equal to yi, and the entire thing the whole square. Okay, and now apply Jensen's inequality. I mean Jensen's inequality in the sense the thing, this thing in the red here, right, which we just argued. So now if you apply here, you get that this is less than equal to n times I equals 1 to n probability that xi not equal to yi the whole square. Okay, and so now, right, so we started with this here, and we ended up with this. So basically what we have argued is that the expected Hamming distance between x and y, the square of that, by n is less than equal to I equals 1 to n probability that xi not equal to yi the whole square, or probability xi not equal to yi square. Okay, so let's see. So yeah, this seems to be option C. Okay, B is strict inequality, so that is not true in general, and D is equality in the other direction, so this is also not true. Okay, so let's go to question number 3. Consider the same setting as in question 2 above. Which of the following are true? So for every coupling we have, okay, so what did we have in question number, okay, the thing we derived in question number 2 was that the expected Hamming distance x comma y the whole square by n is less than equal to I equals 1 to n probability that xi not equal to yi square. Okay, which is same as expected Hamming distance is less than equal to square root n. Let me take two small square roots instead of one big square root. So square root n square root I equals 1 to n, probability xi not equal to yi whole square. Okay, so now what do we know about this quantity on the second inside the second square root? Okay, we know that this quantity here. Okay, so till now what we have is that this entire equation, that expected Hamming distance is less than equal to square root n times the square root of sum of square of probability, sum of square of disagreement on each coordinate, probability of disagreement on each coordinate, right? So we have this with for every coupling P. So we did not assume anything special about this broad P here, right? So this inequality is true for every coupling, and now we know that there exists a coupling, there exists some P, right? This broad P, such that this thing, the probability, the sum of probabilities, the sum of squares of probabilities of disagreements, right? This is less than equal to what is that, 1 by 2 the KL divergence between Q and P. Okay, and why is it Q and P? So this the Q with respect to P. So P here is the independent thing. So x1, xn, these are from like P, right? And Q is something which is absolutely continuous with respect to P. So this is the order in which we take the KL divergence. Right, so P is a product distribution. So this is important in this. I think we use the fact that P is a that x1 to xn are independent, right? Basically, P is a product distribution, and Q is something which is absolutely continuous with respect to it. And then there exists a coupling P. So this is what is known as Marton's coupling. Okay, so what this means is that, okay, let's look at the options. For every coupling we have, okay, so this is not true, right? For every coupling, this thing which I'm highlighting or which I'm circling with this, wait, why is this not working? Okay, which I'm circling with this black thing, right? So this is true for every coupling P, right? But relating it to the KL divergence between Q and P, that for that we need a special coupling. So okay, B is for every coupling we have this. So this is not true because we know that there exists a coupling for which this happens, right? So so B is also not true. C is true. So there exists a coupling such that, okay, so there exists a coupling. So between P and Q, right? There exists a coupling. So this is that Marton's coupling. So Marton's coupling gives us that expected Hamming distance is less than equal to square root of n by 2 into KL divergence. Okay, and D is none of the above. We saw that C is true, so D is correct. So question number 4. Consider the same setting as in question 2. What was question? Okay, question 2 is what we saw just now. Question 2 and 3. Let A be a subset of script x to the n such that probability of A is strictly greater than 0. Okay, so and let PA be the conditional distribution of x given x belongs to A. Right, so that is why we needed this strict greater than 0 thing, so that we can condition on this event. Okay, then which of the following are true? So we are interested in distances between conditional distribution and the actual distribution. So what is the distribution P? Okay, so we have right, we have this script xn, right? So this is a set, and And so what P will do is that like, so for every X in this set, right? Uh, this P assigns to, to, to every X, we have this PX, right? Which defines the PMF. So now we want to see what value does PA assign, right? So PA of X is what? It's basically probability that X is equal to X given X belongs to A. Okay, so this is what we mean when we say in the question it says PA be the conditional distribution of X given X belongs to A. So this is what we mean. And we know that this is equal to probability of X equals X intersection with probability of X given A by probability of X given A. And this is why we needed that probability of X given A to be strictly greater than 0 so that we can do this. We can do this conditioning. So basically we can divide by X given A. And what would this be? This would be, so two cases. This would be probability of X by probability of A, right? So what probability of X belongs to A is just probability of A. Okay, so all these are like probabilities. So I'll just write PR everywhere. Probabilities by probability, and this P probability. So probability of X belongs to A is P of A, and probability of X equals X, and X belongs to A. So if if X belongs to A, so if X belongs to A, small x belongs to A, then this intersection just becomes probability of X equals X. Right? And if X doesn't belong to it, then this numerator becomes 0. So we have 0 if X doesn't belong to it. Okay, right? So we had this big set script X to the power to the n, and we had this subset A which had strictly greater than 0 probability, and we conditioned on this probability. So after conditioning, what happens is conditioned on that X belongs to A, so we get a new distribution P of A, and P of A is 0. So P of A is 0 here, right, in A complement. And in A, if we have an for X in A, this just becomes Px by Pa. So we are dividing by something less than 1. Pa is less than 1, right? Less than equal to 1. So which means that Pa of X is greater than equal to P of X, the original probability for X in A, right? For all X in A. Okay, so let's see. So what we want to compute the total deviation distance, first total variation distance between PA and P. Okay, and this should be clear from the lectures that so there are many ways of computing total variation distance, but one of the ways is that just sum over, so these both are probability distributions on X power n, right? So sum over all X in X power n such that PA of X is greater than equal to P of X. Okay, of PA of X minus P of X. So this is one of the formulas for K divergence for total variation. Okay, and we know that this, I mean, for all X where P of X is greater than equal to P, where PA of X is greater than equal to P of X, this is exactly X belongs to A, right? Because for X not in A, uh, we have like PA of X becomes 0, right? Uh, and for X in A, P of X is greater than equal to P of X. Okay, so this is okay. So we have X in A, PA of X minus P of X, which is what? So okay, so if you sum PA of X, right, over all X in A, so that would just become 1, because PA of x is only supported on A. And then if you sum P of x over x belonging to A, that just becomes P of A. So we have 1 minus P of A. Right? So A is incorrect, but P is correct. And now we want to compute the KL divergence between PA and P. So, okay, so what is the condition for computing KL divergence? We want that PA should be absolutely continuous with respect to P. What this means, what this symbol means, right? What this statement means is that if P of an event is 0, then PA of that event should also be 0. Okay, and this is true. So if the original probability is giving 0 probability to an event, right, you cannot make it non-zero by just conditioning it, because conditioning it just makes it P of x by P of A, as we saw here above. Okay, so this is always true. Right? So PA is absolutely continuous with respect to P. So we can compute the KL divergence. So let's compute KL divergence of PA from P. So this just becomes x in A, or okay, let's just say x, okay, belonging to this xn, PA of x log of PA of x by P of x, right? And we know that PA of x by P of x, PA of x is what? It's just P of x by P of A, and then by P of x. So this cancels P of x, and we have 1 by P of A. And then what we'll have is, okay, so basically log 1 by P of A, and then this summation x in xn PA of x, right? And this we know is, I mean, we are summing PA over all x's, so this should be 1. So we are just left with log 1 by P of A. Okay, so C is correct and D is incorrect. Okay, question number 5. So let PA be the distribution as in question 4 above. So PA is that conditional distribution, right? Conditioned on x, right? We have conditioned on this event. Let Z be a random variable distributed as PA. Okay, so Z is sampled from PA, suppose, and X be distributed as P. So X is distributed as P. Let the Hamming distance between X and A, so X, right, it will be a random variable, so but it will belong to this set Xn, and A is a subset of Xn, right? Be the Hamming distance of X from the set A. Okay. And how do we define this Hamming distance of a vector x from a set A? Is it's like the minimum of Hamming distance between x and all y's belonging to A, right? So if this is x and this is a set A here, what is the distance between x and set A? Just find some y in A which is closest to x, and right, that is the distance between this x and the set A. So which of the following are true? For every coupling we have, okay, so let's see. Right, so if we have this Hamming distance between x and A, right? And we have this Hamming distance between x and z. Okay, and P and Z is coming from PA. PA is supported only on the set A. So when you sample Z, Z will also always belong to the set A. So what we can say that this Hamming distance between x comma A will be less than equal to Hamming distance between x and Z. Right? This is true because for finding Hamming distance in x and A, we find some point in A which is closest to x. But here we just know that Z is in A. We are not necessarily Z may not be closest to x basically, right? And Z belongs to it. So this is correct. Um, right? So even if you now take expected value, so right, this is true for all z, for all x comma z, right? So if you just take expectation on both sides, this would also be true. Okay, so left hand side was a random variable which depended just on x, so some f of x, and this was a random variable which depended both on x and z, and right, some g of x comma z, and so we had this one random variable is less than equal to the other random variable for all values of that random variable. So in expectation also we would have this inequality, right? So straight away we can say that option A is correct, and this is true for every coupling. So when we took this expectation, we took, especially on the right hand side, when we took the expectation, we took it with respect to any coupling between x and z, right? It's true for all coupling. B is incorrect. C for every coupling. Okay. Now, um, okay. So what did we derive in? Let's go to question number 2. Okay. So question number 3. Question number 3, we had this, right? That there exists a coupling, that Martin coupling, for, right? And on the left hand side we had x comma y, and we said that there exists a coupling between x comma y such that this happens, that Kerr divergence condition happens. So similarly here, we have two random variables x and z. Okay, x, and so there exists a coupling p, right? And this would be the Martin's coupling between x and z such that the expected Hamming distance between x and z is less than equal to square root of n by 2 Kerr divergence between what? Between between PA and P. Okay. And we know that the Kerr divergence between P and P is 1 by PA. This was what we derived the last, log 1 by PA in the last question. So D is correct and C is incorrect. Okay, so we had this Hamming distance between X and a set A. Then we related it to a Hamming distance between X, Hamming distance between two random vectors X and Z, right? Where Z is coming from a distribution which is absolutely continuous with respect to distribution of X, and so now we can apply Martin's coupling between X and Z to get this thing here. Okay, question number 6. Let P be a distribution on a set X with metric T. Okay, so now we are entering into that isoperimetry domain, the lectures on isoperimetry. So let P be a distribution on a set X with metric T. Uh, for a for a set A, define FA as FA of X is the distance of X from set A. Okay, we have already seen this. So, and M of FA X denotes median of FA. Okay, so the question is, yes, question is P of A. Okay, so we want to find basically median. Wait, let me. So median of FA, right, of X. I mean, I'll make a bracket like this so that it looks like expectation. I mean, this is a deterministic quantity, median of Fx, right? And we want to see what that median would be depending on what this PA is. Okay. So, okay, so FA of X is what is distance of X from set A. So, which means if X belongs to A, then FA of X would be 0. Okay. Okay. So suppose P of A is small p, right, then fa of x, which is a, so we consider it as a random variable, fa of x is equal to 0 with probability p, right, and it is greater than 0 with probability 1 minus p. So it's equal to 0 with probability p basically. Okay. So now if p of a equals half, then what we have is that fa of x. Okay, let's define y as fa of x. So probability of y, so y probability of y equal to 0, right, would be half. Okay, so what this means is that probability of y greater than equal to 0 is greater than equal to half, right? Because equal to 0 is half, so greater than equal to 0 would be greater than equal to half. And probability of y less than equal to 0 is also greater than equal to half, right? Because probability of y equals 0 is already half, and less than equal to 0 means you are adding more elements, and so that is greater. And this is, so what this means is that 0 is a median. So median may not be unique. Okay, so 0 is a median. That's why we say a median. So median's definition is some quantity for which being greater than equal to that quantity is also more than half the probability, and the probability of being less than equal to that quantity is also greater than equal to half. Okay, that's how we define median. Right, so for half we know that, okay, the median would be 0, so this b is correct. Um, but even if so, suppose if PA is 3 by 4, right? So what we have is probability of y equals 0 is 3 by 4. Okay, right? So again, if you see, the probability of y greater than equal to 0 would be greater than equal to 3 by 4, and 3 by 4 is greater than equal to half, right? So again, probability of y greater than equal to 0 greater than equal to half, and probability of y less than equal to 0 is also greater than equal to 3 by 4 is greater than equal to half. So if p, so again 0 is a median, right? Uh, so basically if you take any prop pa which is more than half, more than equal to half, uh, the median of fa, I mean 0 would be a median of fa in that case if probability of a is more than equal to half, greater than equal to half. Okay, so bcd and bcd are all correct. Okay. Right, and a if you see a will not be correct in this case. Median, so median, if in terms of cdf, right, if this is a cdf of a probability distribution, you want to see where does it cross half, right? So what is happening is that y is a random variable, which is the distance between x and a. So y is a random variable which is, first of all, it's greater than or equal to 0 always, and y is equal to 0 with probability say 3 by 4. So what is happening if you draw the CDF, it's like 0 0 0 0, and suddenly there is a jump at 0, right? And it's so this is 3 by 4, right? So in terms of CDS, where does it cross half? Half would be somewhere here. It crosses at 0, right? So basically 0 becomes a median, remains a median in that case. But if it's 1 by 4, then this would be the case. You have 1 by 4 here, and then maybe it increases to 1, and somewhere here the median is strictly greater than 0, because um, right, for because strictly greater than 0 for with probability 1 minus b. So basically a is incorrect and all the others are correct. Okay, question number 7. Let P be a distribution on a set X with metric D. Let F be a function satisfying this Lipschitz condition that fx minus fy is less than or equal to 3 times distance between x and y. I mean distance in the sense absolute value. For every x comma y in X. Let B be this set. Let B be this set where fx is greater than or equal to. So straight away we know that probability of B is greater than or equal to half, right? By definition. Because the probability of fx being greater than or equal to median of fx, that has to be greater than or equal to half. Okay. And let bt be the t blow up of B. So yeah, so if this is B, suppose t blow up would be just increase, right? Basically increase the boundary by distance t here. Okay, which of the following are true? Okay, so bt is a subset of something bc. Okay, so it's b. We want to argue about if x belongs to b of t implies something must happen, right? So or implies something, implies something, right? So then probability of bt would be, so which means bt would be a subset of this something, right? Okay, so right, so we know that, so if this is b, we know that b is defined as all x such that f of x is greater than or equal to median of f of x. Okay, and then we have this t blow up here. Okay, so by definition, if you take any point here in the t blow up, suppose this point here, we know that fx has to be less than median of, okay, because this point, the t blow up, this point which is not in b but in the t blow up of b, that would be, that point is in b complement, and by definition b complement would be all such x where fx, okay, I'll not write it, but b complement would be all that x so fx is strictly less than median of fx. Okay, okay, and but note that okay, so this condition is true that fx is less than median of fx, but so let's say this point is y, so y, okay, fy is less than median of, but what we have is that the distance between y, so distance of y from b is less than equal to t by definition, okay, because y is in bt, which is the t blow up of b. Okay, so the distance is less than equal to t, distance of y, and so so what this means is that if, so which means there is an x in b such that distance of y comma x is less than equal to t. Basically y minus this absolute value is less than equal to t. Okay, so there exists some x in b, and now we know that since x is in b, fx is less than equal to median of f of x. So fx is less than equal to median. So this would imply that fy is less than equal to median of fx plus 3t, right? Because of this Lipschitzness condition. So we know that f of y, so sorry, I think all the inequalities are reversed. So yeah, so we know that fx is greater than equal to, right? This is by definition of b. Fx is greater than equal to median, and so Fy would be greater than equal to median of fx plus 3t. Okay, so this, suppose this line is the median. Okay, and we know that, yeah, this is something, right? Suppose this is the function fx, and so we know that this set, right? So this set is B, because here fx is less than equal to median, right? Okay, uh, and for a t blow up of B, what we are saying is that outside this B, fx would be less than median, but fx would not be 2 less than median, so it would be like fx would be greater than median plus 3t, and this is by Lipschitzness, right? So fx in the t blow up, we are saying that, suppose this line is m minus 3t, so in the t blow up, the value of f would be above this f, m minus 3t line. Okay, right? So what this condition, what this Lipschitzness condition allows us to do is that we are going from this function, we are relating the domain to the function value, right? So we want, um, so we have this, that there is this domain bt, and in this domain we have that fx fy is greater than or equal to median plus 3t. Okay, I mean, this should be minus 3t. So yeah, all right. So this was covered in lectures as well, so you can take a look if you're a little confused. But yeah, the thing is that since from going from B to BT, you're not changing by a lot. So even though fx would be less than m of fx outside B, but if you're still in BT, it cannot be too less because you're not very far. Okay. Yeah, and so A is correct, right? And yeah, all 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 the other things may not be correct. So A8. So let x be x1 comma x2. X1 comma x2 are independent standard normal. Let h be x1 comma x2 such that x2 is greater than or equal to x1. So let's draw this. So okay, let this be the x1 axis, let this be the x2 axis, and so the h set is everything above this line, right? Let ht be a t blow up of h. So ht would be everything above this line, but also everything above, right, this line, suppose, right? And the distance, this distance here would be t. So this, we are in the Euclidean space, so everything is the usual distance. So in particular, this would be like root 2t. This will cross this. Okay. ht be a t blow up. Which of the following are true? Okay, so yeah, so we know this thing, right? So okay, so we know that this Gaussian random the standard normal is rotation invariant. Okay, so what that means is that if we want to, the probability of this thing, right, above this line will be the same as if we just rotate this line, right? So if we just rotate this line so that it coincides with the y-axis, so then it would be this, right? And the probability of both the regions are same. It's half basically. So you can formally prove it using change of variables and all that, but right, this is the standard property of an important property of standard normal, that it's rotational invariant. Um, and so what that means is that you can rotate everything and then start arguing. So right, So you can consider again this as x1, x2 axis, and again this would be like a t blow up. And here it's easy because this would just be t, right? A t blow up would be, right, increase everything by t. And right, and so probability of so C is correct. So for instance, so probability of HT is equal to probability of x1 less than equal to t. So x1 less than equal to t in this diagram is what I'm marking with red now, right? Everything to the left of this line, and right. So this is x1 axis. So x1 less than equal to t, and x1 and x2 are identically distributed. So it would also be x2 is less than equal to t, right? So so probability of HT basically is just probability of x1 less than equal to t. X1 and x2 are identically distributed, so this would also be probability of x2 less than equal to t. And if ht probability of ht is equal to probability of x1 less than equal, it also means it is also greater than equal to probability of x2 uh, is less than equal to t, right? So A is also correct, and B and D. Okay. So D might be a bit tempting because if you take this blow up here, right? So I will start writing with black now. So this point here is root t. The t blow up will cross this thing at root t to root 2t here, because we are t in this direction. So if we straight down from the origin, it will be root 2t here, right? But so probably, so what would be this, the equation of this line, the black line? It is x2 is greater than equal to x1 minus root 2t. So what we have is that probability of ht is same as probability of uh, x2 is greater than equal to x1 minus root 2t, which is same as probability of x1 minus x2 is less than equal to root 2t, right? And so basically what we are claiming by rotational invariance, this is also equal to probability of x1 is less than equal to t. This is also equal to probability of x2 is less than equal to t. And right, and this comes from rotational invariance of standard normal. Standard normal has all same variance in all directions, so that is why it's rotational invariant. Okay, question number 9. Let x be all this be distributed as standard normal again. Let f be a function such that fx minus fy, again we have this Lipschitz condition. Let a be the set, again we have similar thing here, all the x's where x is less than equal to, where fx is less than equal to median of fx. And let at be the t blow up of a, which of the following are true. Okay, so similar to what we have seen earlier. So we have this set A. This set contains, I mean, if you take any x here, what we'll have is that fx is less than equal to median of fx. Okay, and now consider a t blow up. Okay, so now for any point y, we have that fx is y outside this A but inside the blow up. It's like fx is greater than m of fx, which is by definition of A, since y is in A complement, right? But since y is not very far from the set A, we can argue that fx is, so it might be greater than, I mean it is greater than median of fx, but it is has to be less than equal to median of fx plus 3t 3t, and this is again because of this Lipschitz condition. And so even though you have to be bigger than median, but you still have to be less than equal to median plus 3t, because in A you are less than median, so in AT you have to be less than equal to median plus 3t. So again you see that x such that fx Um, okay. So first, let's see what's the question. So which of the following are true? Probability of AT is less than, okay. So now this is where we have this isoperimetry inequality, right? So what isoperimetry allows us to say is that what is isoperimetry? I mean the exact isoperimetry thing where, right, we have that for a given volume the sphere has the smallest thing. The sphere has the smallest surface area, right? In the Euclidean geometry. But here we are in the Gaussian geometry, and again we saw in the lectures that for Gaussian hyperplane, the half space takes the role of sphere. So in the Gaussian, suppose you had this set A here, right? And suppose probability of, and you had this blow up of A, right, and all that, and suppose probability of A is greater than or equal to half. Okay, this is some condition we have. Uh, what what we are saying is that, and all this is in the Gaussian domain. In that case, take this half space, right, and construct this half space so that, suppose this is the half space, and let's say this is H, this half space, the shaded region, such that P of H is same as P of A, right? So where this probability is the standard normal, right? The both probabilities. So we had this set A here, but right, and we want to argue about the T blow up of A. So instead, what we do is take this half space here, which has the same probability of A, and consider a T blow up of that. Okay, and then what isoperimetry says is that the T blow up in the half space is the smallest, right, among all the sets A which with the same probability as this half space, right? So which means that, suppose this T blow up is HT, and here the T blow up is AT. So what this means, or what we are saying, is that probability of AT would be at least uh, probability of HT. So half space has the smallest surface area. So you can treat this thing here, what I'm shading as red, right? This is kind of a surface area as t goes to 0, right? So we saw the definition of surface. So the hyperplane has the least surface area, and so probability of AT, right? So this thing, when you do this T blow up of A, this would be more than A will have more surface area than the half space, and so the total probability of the blow up. So we already had that probability of A is probability of H, and right, and the surface area of A is at least surface area of H, because surface area of H is the least, right? So totally this gives that probability of the total blow up of AT is greater than or equal to probability of uh, this HT. Okay, and now again, since this is standard Gaussian, we have this rotational invariance. So why take these difficult half spaces? Take a simple half space. Um, so right, so if we had this thing here, right, if we have, suppose this half. Okay, so this figure I drew was this thing. It's incorrect. Okay, so I mean, yeah, what I argued is correct, but what we want to say is that um, so this thing PA equal to PS, this may not be true. This need not hold, and we still have this condition here. Okay, so and for that we require that PA be greater than equal to half. So for PA greater than equal to half, suppose there is a set A, we have that P of AT is greater than equal to P of ht, where h is half space with probability of h equal to half. Okay, so you just have to so you can consider this half space. So since Gaussian is rotationally invariant, you can consider this half space here, suppose, right? And so to t blow up again would be this ht here, and so we have this thing here. All right, so what this means is that P of at is greater than equal to, so if we from here we get that probability of x1 is less than equal to t, where x1 is standard normal, right? So x1 x2 is standard normal, and yeah, okay, right? So for instance C is correct here, right? And we know that we already know that if you are in AT, so x is AT implies that fx is less than equal to median plus 3t, right? And so B would be also correct. Okay, which means that AT is a subset of all the x's such that x fx is less than equal to m plus 3t, right? So which means probability of AT is less than equal to probability of, right, whatever this thing. So right, and yeah, T can be a bit confusing, but it's not correct, and A is also not correct. So we have three Lipschitzness here because of this three here. Right. So consider the same setting as in question 9 above. Let T be bigger than 0. Which of the following are true? Okay. Um, right. So probability of fx greater than, so median plus t, right? So we just saw that this, okay, so let's see what, let's write down what we saw in question 9 above. We had inequalities on both sides. First of all, we had this probability of AT is less than equal to probability that fx is greater than equal to median of fx plus t plus 3t, right? We also had, and so this the, this came from Lipschitzness, right? Three Lipschitzness, and we also had the P of AT is greater than equal to probability that x1 is less than equal to t. Okay, so this came from isoperimetry and rotational invariance of Gaussian of standard Gaussian. Okay, right? And if so, okay, so if you just replace t by 3 for this question, so t by 3, right, and this 3t by 3 becomes 3t by 3, so just becomes t. So now if you, so we can relate this to this, the extreme right to the extreme left, right? All the equalities are in the right direction, so in the consistent direction. So we have probability of fx is greater than equal to median of fx plus t is what? It's greater than equal to probability of x1 is less than equal to t by 3. Okay, so uh, yeah, this is correct, and and now x1 is just the standard normal in one dimension, standard normal in 1D, right? X1 is that. So this is just this is just this CDF of the standard normal. So right, this is CDF of n01, this phi here, which means that probability of fx Yeah, what was A here? So A was fx is less than equal to median of fx. Okay. Yeah, so this would be less than equal to, this would be less than equal to, right? So now take complement, okay, which means probability of fx greater than equal to m of fx plus t is less than equal to 1 minus phi of t by 3. Okay, so let's see, fx greater than 1 minus phi of t by 3. Okay, yeah, so C is correct. And if C is correct, D is also correct, because yeah, t by 6 we know is less than t by 3 because t is greater than 0. And so if C holds, then D also holds, because CDF is the increasing function of t. Okay, so you see how we are able to get this concentration inequalities, concentration around the median, right? By using isoperimetry. So now what is allowing us to go from this, from going from, okay, what is allowing us to go from this function space, I mean arguing about function, to arguing about domain in the, so let's see, so x belongs to this script x, right? And we are arguing about things like fx greater than median of fx plus t, things like that. So we are arguing in the f domain, uh, but Lipschitzness allows us to relate it to some. So here Lipschitzness allowed us to relate it to at3 t blow up, t by 3 blow up of a, where, right, which is a subset of this x, script x. And so now we are again in the x domain, and then we can use isoperimetry that for any set in x, half space has the least surface area if you're in the Gaussian thing, right? If x has the Gaussian measure, and so on and so forth, right? So from, so relating this function value and getting to a set in the domain, that requires Lipschitzness. I mean, there can be other conditions, but you basically want to relate this function condition to a set in the domain, right? To a blow up of a set in the domain, and so that is why we had this Lipschitzness condition throughout this discussion on isoperimetry. Okay, so we are done with all 10 questions. So yeah, I don't have anything else to discuss. So I think from next week, I think week 7 would be taught by Professor Himanshu Tyagi, where, so we are done with isoperimetry and transportation. So the next week will cover, I think, log Sobolev inequalities, right, and various equivalent forms of log Sobolev inequalities and relating it to information theory and all that. Okay, so yeah, so I'll see you next week. Bye.